So we have already learned how to design digital circuits by using gates. Gates are made of transistors. And on the other side, NAND and NOR gates require less number of transistors. So first, in this topic, we would like to start with NAND NOR implementation. Then we'll study a particular principle which we call duality principle. Then a theorem, and the name of the theorem is consensus theorem. Okay, so let's start with NAND implementation. So we'll see that any logic circuit or any logic function can be designed by using only NAND gates. Any Boolean function can be designed using NAND gates only. And how do we do it? So by applying the De Morgan theorem. So we know that there are two versions of the De Morgan theorem. So we saw the De Morgan theorem in the case of two variables. But if we have many variables, for example, so if we have A1 plus A2 plus up to n variables, and then the whole prime, then we can write it A1 prime times A2 prime, then up to an prime. So the De Morgan theorem is applicable for more than two variables as well. So now how do we implement a function by using NAND gates? So we apply the De Morgan theorem in order to eliminate all the OR operations from the function. Let's see this with a couple examples. So the first example that we have, so we are given a function and we need to implement the function by using only NAND gates, and the function is a b plus a b prime c plus a b prime d prime plus e. So in order to implement this function by using NAND gates, we need to eliminate all the OR operations. So how many OR operations we have? 1, 2, 3. 3 OR operations we have. Now we are going to apply the De Morgan theorem so on the whole equation, on the whole expression. And how do we do that? It's AB plus AB prime C plus AB prime D prime plus E. Now, in order to apply the De Morgan theorem, we need a prime here, but we just cannot put a prime anywhere. So if we want to put a prime, then we need to put another prime, because we know that prime get cancelled. A prime equals to A. So now, applying the De Morgan theorem in the inner prime of the equation, then it will give us a b prime then A, B prime, C prime plus, oh no plus, we don't have any plus here, times A, B prime, D prime, then A prime, then E prime. Okay, so then we still have another prime here. Now, so in this function, we don't have any OR operation, only the AND operation, and easily we can implement this function by using only NAND gates. Let's do it. So how many inputs we have? A, B, C, D, E. So we have 5 inputs. 1, 2, 3, 4, 5. A, B, C, D, E. Now first we want to implement that guy. It's A, B prime. So we need an AND gate for that. So here we get A, B prime. Now, so for the second one, so we already have A, B prime, then A, B prime, C prime. So we need another NAND gate. And the first input is A, B prime, and the second input is C. So here, so we have A, B prime, C, and a whole prime. Okay, so we have implemented the first term, we have implemented the second term. Now we want to implement the third term. So for the third terms, A, B prime, we already have that. Now we need D prime. So we need an inverter, and the inverter also must be made of the NAND gates only. This we get here D prime, then an AND gate, another NAND gate. So A, B prime, so we have this A, B prime, and D prime. So here we have A, B prime, D prime, then a prime. Now E prime, oh, it's not E prime, yeah, E prime, so E prime. So for doing E prime, so we need another NAND gate, and after doing that we get E prime. So how many total we have? AB prime, and AB prime, C whole prime, AB prime, D prime whole prime, E prime. So 1, 2, 3, 4. So 4 terms we have. Now we need an AND gate, 4 inputs NAND gate. The first input is AB prime, and let's do it. This AB prime, then the second input is AB prime, C whole prime. We got the second input. The third input AB prime, D prime whole prime. The fourth input is E prime, so we got the E prime. And the output is the function. So that's how, so by using the De Morgan theorem, we can implement any function by using so only NAND gates. Let's see another example, and this for this example, implement the following function. Using NAND gates only. what is the function that we have been given? Is f equals to a b plus c. And we know that in order to doing so, we need to eliminate the OR operations. We have only one OR operation in this function, so this is pretty easy. AB plus C. We need to apply the De Morgan theorem, and we need another complement here. So now applying the De Morgan theorem will give us AB prime times C prime. Then we have a whole prime. Okay, that's it. Now there is no any OR operation in this circuit, and we want to draw the circuit. 3 inputs we have: A, B, C. And the first one is AB prime. For doing this AB prime, we need a NAND gate. Here we get A, B prime. Then we need C prime. So then we need another NAND gate here, C prime. Then we got AB prime, we got C prime, then another NAND gate. The first input is AB prime, the second input is C prime, and we get the function. Now we start working with NOR implementation. This means that any logic function can be implemented by using NOR gates only. So in this case, we are also going to apply the second version of the De Morgan theorem in order to eliminate all the AND operations from the equation. So now the second is if we have A1, A2, A3 up to AN number of Boolean variables, and applying the De Morgan theorem will give us a 1 prime plus a 2 prime plus, that's the we go, and eventually you have AN prime. So this is the De Morgan theorem, and we want to apply this for the purpose of NOR implementation. Let's see this by using an example. Okay, so the first example that we have, we are given a function and the function is f equals ab . So in order to implement this function by using only NOR gates, we need to eliminate the AND operations. How many AND operations we have in this function? So only one AND operation, AB, between A and B. So now what do we do? So we apply the De Morgan theorem here in AB. So in order to doing so we put here on complement and then another complement plus C. So now what do we have here? A prime plus B prime after applying the De Morgan theorem, and we also have a prime plus C. Now we know, so we can implement A prime by using a NOR gate, B prime by using a NOR gate, and also A prime plus B prime all using a NOR gate. Then so we got that NOR implementation, and now then what can we do? So we actually we have this OR operation. So in order to make it NOR, then we can add more complements like A prime plus B prime prime plus C. So this is something that we already have. So now we want to add another complement. Then after that, so one more complement. So now we want to draw the circuit. So let's start with A prime. So how to implement A prime? So if we have a NOR gate, we have A, then this will give us A prime. Similarly, B prime, and with the NOR gate, we have B, then B prime. So now A prime, B prime, whole prime. So we need another NOR gate here, A prime, B prime. So now what do we get here? A prime plus B prime whole prime. So you got that piece. So now so we need another NOR gate for the entire term here. And so how do we do that? We have the NOR gate, and one input is that, and another input is the C. So there we get A prime plus B prime prime plus C prime. This is something that we got here, but there is another complement here, another prime. So we actually need an inverter. So this is the final function. So that's how we can implement any function by using only NOR gates. Now we study the duality principle. So the duality principle says that every Boolean equation has a dual form. If the original Boolean equation is valid, then the dual form is also valid. And now the question is how to find the dual form. So in other words, we write that a Boolean function remains valid if we do for replacements. If we replace the following things, the number 1, 2, 3, and 4. The first one, so in the Boolean function, we replace all the OR operations by using AND operations. All the AND operations by OR operations. Then 0, 0 by 1, and 1 by 0. So if we do this 4 replacement for any equation, then we get the dual form of the equation. If the original equation is correct, then the dual version of the equation is also correct. Let's see this by a few examples. The first example that we have is we are given an equation A plus B, A plus CD, and we know that the equation has a left hand side and also a right hand side. A plus B, C, D is a right hand side. So now if we apply the duality principle here, So if we have first A plus B, and the relationship between A and B is plus, so that will be times now, and then this times will be plus now. So AB plus A times C plus D equals A times B plus C plus D. So if the first equation is correct, then the second, the dual form of the equation, is also correct. Let's see another example here, that we have the equation A plus A prime B equals A plus B. So then the dual version of this equation would be A times A prime plus B equals AB. Another example, A plus 1 equals to 1. Then the dual version would be A times plus is replaced by times, and then 1 is replaced by 0 equals to 1 is again replaced by 0. So now we study the consensus theorem. So this theorem says that AB plus A prime C plus BC equals to AB plus A prime C. So is it possible, here we have AB, we have AB on the other side, so we have A prime C, we have also A prime C in the other side, but this guy is extra, so BC. Now the question is it possible? It's kind of x plus y plus z equals x plus y, right? So I don't know so if it is possible or not in algebra, but in Boolean algebra this is possible, and this is called the consensus theorem. And how do we prove that? Let's start with the left hand side. So we have A, B plus A prime C plus BC. And anyway, we want to eliminate the term BC from this expression, and if we can do that, then we prove it. Let's write AB plus A prime C. And what is missing in BC? A is missing. So we can actually write it A plus A prime. We know that A plus A prime is 1. So 1 times BC. So we can write it this way. Then AB plus A prime C plus, now we apply the distributive law, ABC plus A prime BC. Now consider these two, AB and ABC, and if we have AB, then we have 1 plus C plus, let's consider that guy, A prime C, A prime BC. So if we have A prime C, then 1 plus B. We need space now. So we know that 1 plus C equals 1, 1 plus B is also equals to 1. So we got AB times 1 plus A prime C times 1. And anything times 1 equals anything. Now we see here that this is actually the right hand side of the equation. So this is the right hand side. So the consensus theorem is proved. So now, what is the dual version of the consensus theorem? So if we apply the duality principle in this theorem, then what do we get? So we get from here a plus b, then this plus becomes times a prime plus c times b plus c equals to a plus b times a prime plus c. A prime plus c. So in exam, I may ask you to prove this guy, the dual version of the consensus theorem. Okay, anyways, I can ask the first version or the second version of the consensus theorem. Thank you.